Last time we built one attention head completely by hand. Query, key, value, a softmax, a weighted sum. It worked, but a real transformer doesn't run one attention. It runs many side by side every single layer. Today we take that one head, multiply it and wrap it in the scaffolding that makes deep networks actually trainable, residuals and layer norm. By the end, you'll have assembled the real thing, the transformer block. We're still in the build stage of our pipeline, but this is the deep end of it, the engine room. Here's the one head we built last episode. One query, one set of keys, one weighted blend of values. Powerful, but it's looking at the sentence through a single lens, one relationship at a time. Real transformers don't settle for one lens, they open 8. That's multi-head attention. Instead of one attention, you run several in parallel, 8 here. Each head gets its own little query, key and value projections, so each one is free to learn a different relationship in the same sentence, 8 independent readings computed at once. And they specialize. One head might learn grammar, which verb belongs to which subject. Another tracks long-range meaning across the whole sentence. A third just locks onto punctuation. Each head produces its own output vector. We line them up, concatenate them, and project back down. So the next layer sees all 8 perspectives fused into one. But attention has a blind spot. It treats the sentence as a bag of words. It has no idea which word came first. Dog bites man and man bites dog look identical to raw attention. So before anything else, we add position information to each word. We literally add a "this is position 5" vector on top of the word's embedding. Now order is baked in. Next, residuals. Watch what we do. We take the attention output and we add the original input back to it. Why? Because deep networks forget. Stack enough layers and the gradient fades to nothing on the way back. A residual gives the gradient a highway straight through. Every layer can fall back on, just pass it through unchanged if that's what helps. It's the trick that lets us go deep. Then layer norm. After all that adding and mixing, the numbers in each vector can drift, some huge, some tiny. Layer norm recenters and rescales every vector, so the next layer always gets clean, well-behaved input. Normalize, then continue. Add norm, add norm. That rhythm repeats through the whole block. And in the middle, the feed-forward net. After attention has gathered context from across the sentence, the FFN thinks about it independently at each position. It's just 2 dense layers, expand wide, rail U, squeeze back down. Attention moves information between words. The FFN processes it inside each word. And that's it. Multi-head attention, residual norm, feed-forward, residual norm. That is the transformer block. Stack it 12 times, 96 times, and you have GPT, you have BERT. You have the engine behind every model you've heard of. Next episode, we stop drawing it and point it at IMDb and watch it beat the LSTM. Let's build it in Keras, one file, 3 pages, 2 custom layers, positional embedding and the block itself. Then we wire them with the functional API and print the shape. Keras gives us multi-head attention and layer normalization for free, so this is shorter than you'd think. Imports first, tf Keras layers, then our positional embedding layer. It holds 2 embeddings, one for the token, the word, and one for the position. In call, we make a range 0 to 200, look up a position vector for each slot and add it to the token embedding, word identity plus word location summed. That's positional encoding, the learned version. Now the blocks constructor, multi-head attention with 8 heads. Note, keydim is d model over num heads, so each head works in a 16-dimensional slice. The FFN is a tiny sequential, dense up to 512 with ReLU, dense back down to 128, 2 layer norms, 2 dropouts, everything the block needs, declared once. And here's the heart of it, the pattern worth memorizing. Run attention. We pass X as both query and value. That's self attention. And ask for the scores back so we can inspect them. Add the input back, then norm. Run the FFN. Add that input back, then norm. Return the output and the attention scores. Add norm. 6 lines that are the whole transformer. Now assemble constants 20,000 vocab, 200 sequence length, 128 model width, 8 heads, an input of integer token IDs, run them through positional embedding, then through one block, which hands us back both the output and the attention scores. We build a Keras model that outputs both and call summary. Finally, a fake batch, 32 sentences, 200 tokens each, pushed through. Output shape comes back 32 by 200 by 128. Same shape in, same shape out, which is exactly why you can stack these. The summary reads about 2.8 million parameters, and notice almost all of that is the 20,000 word embedding table. The block itself is only about 198,000. And peeking at the scores, head 3 has latched onto punctuation, head 7 onto the subject. The specialization we talked about live, that's the block. Next time, we feed it real movie reviews and let it beat the LSTM we trained back in episode 12.